Stefan, what is this?
This is an FPGA board that I'm using for my experiments.
What is an FPGA?
Well, in principle, an FPGA itself is an integrated circuit that combines a lot of logic gates, and you can use it to build reconfigurable circuits. So just a couple of years ago, so when I started building digital electronics, you would usually start with a breadboard and then put different ICs on the breadboard and wire them with tiny wires. But your circuits sometimes need to be faster or more complex. At some point you either need a lot of space on your breadboard, or you just can't reach the frequencies in which you want to run the actual circuits, like the calculations you can do in digital logic. An FPGA does it a little bit differently. So when you look at an FPGA, let's say under a really big microscope, you see that there are a lot of these logic gates on it. Let's say, for the sake of the argument now, that it's just 9 logic gates. All of those logic gates, they have a so-called routing fabric next to them. And when you want to build circuits, well, you have to connect your different logic gates to one another, right? So let's just say you want to make a digital circuit that looks something like Q is equal to A and B or C. You've got 3 inputs and 1 output. Let's say these are all AND gates and these are all OR gates. On a regular breadboard, you would now have to pick those individual parts. They would also sort of look like these ships, but maybe a little bit bigger. The older ones, you could just push them into a breadboard. But on this FPGA, you can now use transistors to wire up 2 inputs with, let's say, this AND gate, and then you can use the output, use another transistor, go to this AND OR gate, and use, for example, this. Come in here, go there, go up here, then use another transistor here, then you use that output, put that on this wire, maybe route it all the way here. Now, here's your Q, say here is your C, and we've got A and B up here. So these pins would be outside of your actual FPGA package, right? They're like these wires that you can see here, right? They go into the FPGA. Well, now you have a complete circuit that does this one operation. Obviously, a modern FPGA is way more complicated than this. You have like more complex gates, and you have really a lot of them, like hundreds of thousands. But the cool thing about that is that I just drew a couple of transistors. Actually, there are way more, and they connect all of the logic cells and all of the logic gates to this routing fabric. Now, if you would index all of those transistors, let's say this is 1 and this is 2, and then there was a third one, and so on and so forth, you end up with, let's say, a table where you have 1, 2, 3, 4, 5, so on and so forth. You have all of your transistors, and whether a transistor is connected to a specific cell or not is just a 1, 0, 1, 1, 0. It's just a so-called bit stream. And this bit stream you can flash onto the FPGA. By that you reconfigure the whole integrated circuit in a way that it performs your action that you want to have. Obviously, that's a sort of a simple Boolean logic now here, but you can imagine that you can build that way more complicated, right?
What's the difference between FPGA and microcontroller?
When you're using a microcontroller, the microcontroller already has those wirings inside of it. The microcontroller has different operations that are baked into the actual silicon, while the FPGA only has this, let's say, universal logic gates and some memory cells. So the microcontroller is fixed in what it can do, in which operations it can perform. And you use, for example, assembly code or binary code to put that into the storage of a microcontroller, and then the microcontroller just executes 1, 2, 3, 4, like those different commands. But with an FPGA, you basically build your own processor with it. So also FPGAs are a lot of time used to validate processor design. So if you build a new processor, you might try it on an FPGA first because they're so easily configurable. So a microcontroller has a fixed instruction set, a fixed set of operations that is built into it. And for an FPGA, you build your instructions yourself. But you also don't have to use it in this instruction-like way that you use a microcontroller, where you have one instruction and the next instruction and the next instruction and the next instruction. You can have basically multiple processes in parallel that run independently of one another, which is also something that a microcontroller usually does not do, right? You have your instructions that are iterated over, while on an FPGA, you actually configure the hardware, and the hardware just responds to the different input stimuli.
So a microcontroller has fixed hardware and softwares are run on that.
Yes.
And for FPGA is a configurable hardware.
Yes. So you mentioned the term software, and for microcontrollers, we usually call it firmware instead of software. But for FPGAs, we use the term gateware because it configures the gates. When you look at, for example, FPGA code, in the first moment, you could think that it's also a programming language, right? It doesn't look that much differently, but it's actually completely different, because when you compile code for a microcontroller, the result of that compilation process is a list of instructions that you push into the storage or into the flash or whatever. But for an FPGA, you create only this bit stream. You only create these connections. These connections, they're not actually a program, they are a bit stream configuration file. And this bit stream is generated not with a programming language, but with a so-called hardware description language. You're describing how the hardware should interconnect with each other. So there are basically two different teams when it comes to FPGAs. One of them is using a language called Verilog, and the other one is using a language called VHDL. Obviously, there are a couple of other smaller languages that people use, but VHDL and Verilog are the big hardware description languages.
In what cases do people use FPGAs?
That's actually not an easy question to answer, because you can use FPGAs for all sorts of things. As I said before, you can also build your own processor, put it on an FPGA, and then just use the FPGA as if it was a microcontroller or as if it was a desktop processor. Of course, the amount of logic cells that you have is sort of limited, but one of the main purposes, I would say today, is basically evaluating the design of processors themselves. So you build a piece of hardware for a processor that you want to put into silicon later on, but you start by running it as sort of a simulation on the FPGA. But then there's a completely different route that you can take, and that's the route that I'm usually using them for, which is if you're working with physical signals on wires. When you want to, for example, write your own data transmission protocol, or if you have an ASIC, for example, that has an interface protocol, but there is no real microcontroller hardware for that yet. Maybe it boils down to the idea that you want to use an FPGA when you're really timing critical. So you want to make sure that you run at the actual speed of a bus that sends you bits. When you want to make sure that the timing within your FPGA is exactly how you want it to be, because since the hardware itself for an FPGA is so not trivial but simple in some ways, you can calculate how long it takes for, let's say, a bit that comes in on, let's say, the wire B. There comes a bit, and you want to know when you see the answer. At this point, have maybe the B bit, and if these timings here need to be super precise, you can use an FPGA because, or then you probably should use an FPGA because you can run really, really good timing analyses before you actually put the bit stream onto your device. And as long as nothing in the FPGA breaks, it will be always the exact timing. Obviously, there's like a little bit of jitter in it, but in a certain tolerance, it will run exactly as you want it to do, which doesn't necessarily happen on a microcontroller, even though you can run a microcontroller like that, but there are also different things happening on a microcontroller. On an FPGA, everything is in your control, and therefore you can use it for these timing critical processes, or when you have parallel processes where you want to merge signals, right? Because if you get data from two different entities and that data needs to be precisely merged, then the internal timing of the FPGA is also super critical. And because of this timing properties of an FPGA, you usually use them for those things, and when you have really high frequencies.